challenging problem for simulation. It requires a huge amount of computing power. So to finish this topic, I just want to summarize that, of course, classical molecular dynamics is very detailed and it's going to give you rigorous answers, but for certain problems it's too expensive. So we need other approaches, which are approximations that will give you a reasonable answer and that will focus in a parameter range of solution. The alternative model that we're involved in is the continuum model, the continuum approximation of the surrounding water. So you assume that the solvent, the water, you don't model every single molecule of water because we don't really care what the water molecules are doing. We just want the effect of the water molecules in the whole system. So we can consider the effect of the solvent on average. We don't want to know where every single atom of hydrogen and oxygen are in space. We just want the average effect. So modeling the continuum dielectric, modeling the solving as a continuum dielectric is an approach for that. This leads, as I said before, to a boundary integral equation. And for the boundary integral equation, we can use a fast algorithm, which it turns out is also well suited to many cores, not, of course, as well suited as our embarrassingly parallel all pairs interaction, but enough that we can get reasonable speed ups in comparison to, say, something like low order finite difference. Basically, the fast multiple method, the algorithm that we use to solve this problem, is computationally intensive. It requires a lot of computation compared to data movement. And so it's better suited than finite difference, but it's not as well suited as all pairs molecular dynamics. It kind of sits in the middle. Okay? So in the end, if we put these things together, we're going to have this idea of the multiplicative speedups, which is the motivation of my whole lecture today. And this, in fact, is, I think, common to many computation-hungry applications like CFD or many others, where one can think of a three-step approach. First, restructure the mathematical formulation. Think about how you can model the problem in a way that already gives you a increase in performance or increase in ability to obtain a solution. Second, innovate at the algorithm level. So in the first case, for the bioelectrostatics problem, the restructuring of the mathematical formulation is to use the continuum approximation. Well, we're using some physical also modeling there. And then when we get the PDE, solve that PDE with the boundary element method. So we already are getting some increases in our capability by doing that. The next step is to innovate at the algorithm level. So we're going to use a fast algorithm to solve this, which could be an order n squared problem. We're going to use a fast algorithm and solve it at order n, or order n log n. And number three, tune the software for the hardware architecture and obtain the additional speedups that are possible from the GPUs. So this is a three-step approach that I think one can see in many other applications as providing, being an enabling sort of combination. So now let me concentrate on the presentation of the fast multiple method, which is this algorithm that is being used to compute the bioelectrostatics problem in the continuum approximation with a boundary element representation with order n complexity. As I said, the boundary element representation results in a dense matrix vector multiplication. That would be order n squared. We want to solve that with order n. The fast multiple method was originally discovered by Greengard and Rocklin, and this was published in 1987. And it was proposed originally to calculate the interaction of n bodies, for example, in an astrophysical situation where you have n masses interacting with each other. Now, it is a very famous, a very renowned algorithm, so much so that it was listed in this selection of the top 10 algorithms of the 20th century by a couple of luminaries of our field. And in the same league as, say, the fast Fourier transform or the Krylov subspace methods, things that have been very, very important for computational science in terms of algorithms. Now, despite being in the scene for, say, since 1987, 20 years, whatever, the fast multiple method hasn't had the same impact, say, as the fast Fourier transform has had. Now, I would suggest that this is for two reasons. One, the fast Fourier transform is an algorithm which is easier to grasp, easier to understand. And so, people are comfortable teaching the FFT in a course. People are comfortable giving FFT as an algorithm to program or as a part of a didactic experiment, as part of a project for students. Now, the fast multiple method, I don't think anybody would give you that as a homework. Let's say it that way. It's complicated enough that it would take you a whole year to kind of get it, wrap it around your head. So it's not something that, I don't think anybody would actually have the idea of programming the fast multiple method just for learning, just for didactic reasons. When people that get involved with the fast multiple method, it's because they really need it in their application and they're willing to go through the pain, basically. So it's mathematically is a little bit more difficult. That's the first reason. The second reason, I believe, is that there is little power. We forgot something very important. 30-second break. Oh, somebody's going to give me their power. Great. Thank you. See, we prepared, yet we forgot one of the most important things. Thank you so much. Thank you. Teamwork. Oh, and I can see my notes here now for a moment. There. Okay, so I was saying that the first reason is that the fast multiple method is more complicated than the FFT to understand. The second reason is the relative lack of open source tools for the fast multiple method. The FFT, if you want to use your FFT in your application and you're eager to use it, you really don't have to code your own FFT. There's plenty of things out there, right? Open source, or if you want to use a licensed environment, you can know there will, like MATLAB or something, FFT will be probably also available to you. But really, you don't have to code it unless you actually are doing it for didactic reasons, just for the fun of learning. FMM, it's still quite hard to get a hold of some code, some software, some community assets that we could use for our applications. And this is something that I very strongly believe that we have to correct, because it compounds with the other problem, which is that it's a hard algorithm to understand and program. Those things combined together just make it very hard for this algorithm to have the impact that it could have in terms of its enabling capacity. The capacity to reduce a problem that is order n squared to an order n calculation. So let me give you, again, a high-level explanation of the fast multiple method to give you just an idea. And I can give you some references to share in the Google groups. So the fast multiple method solves what's called the n-body problems. For example, in astrophysical gravity interactions of all masses in a galaxy, say. And it reduces the operation count from order n squared to order n. So what we want to calculate is something like that field F there, which is a function of some kernel, say gravity, the gravitational potential, that is a function of the distance between a number of sources. This xi would be all the planets in your galaxy. Y, of course, is the evaluation point where we want to know the result of the field. And to get the field at y, we need to sum the effect of all the sources. So to get the result in one point, we need to do n operations. So to get the result in n points, we would have to do n square operations. The idea first of the fast multiple method is that we're going to cluster together the effects of sources which are far away. And imagine you have a cluster of galaxies or a cluster of stars that is very far away, you can sort of approximate the gravitational field of them without counting every single one, but by clustering them, that effect together. Within a certain approximation, you can actually control the accuracy of that, or know the error that you're making when you do that. And it applies especially if those objects are far away. So first of all, we can cluster those objects far away. Now, if you do that, you obtain, and through all the mathematical tools that are applied for that, you get what's called the tree code algorithm. This results in order n log n complexity. In addition to that, the fast multiple methods does a second step, which is once I've clustered together my far away sources into an agglomerated quantity that represents them all, I am going to transfer that effect to a local region in space and represent that effect somehow with a series expansion, and then for all the evaluation sites that I have nearby, I'm going to just interact with that representation. So you have both a clustering of the faraway sources and of the local evaluation points. That additional step is what reduces the complexity to order n. Broad brush. Now, to be able to do that, you need to know what's near, what's far. That's the first step. So that's where the tree representation, the hierarchical subdivision of space with a tree representation, a tree data structure, allows you to do that. First, suppose in this case you have a two-dimensional domain, which is the black box here, the big black box. You divide it by 4, you have 4 domains. And the tree representation associates a source or a root node to the whole domain, and once I divide it by 4, I have these 4 domains here, these 4 nodes, that represent the subdomains that you've created. You subdivide further and getting with the red lines over here, and you get these nodes, the 4 nodes, red nodes of each that come out of each one, representing the subdomains that you've created, and so on and so forth, hierarchically until you decide that it's time to stop. So you see, we associate this hierarchical division of space to a tree. Now, when you want to know what's near and what's far, suppose I want to evaluate something at this black box over here in the lower left-hand corner, and the near field of that is going to be these light blue boxes around them. And you can see when I look at the tree, what are the nodes in the tree that are associated to those boxes, and you can see that the near domain, one can identify if every source in space is associated to one box, and this one corresponds to one node in the tree, by knowing the relative positioning of the nodes in the tree, one can determine whether something is in the near domain, the yellow boxes, or the nearmost far domain, which are the smaller red boxes indicated by the red nodes here in that I'm pointing to on the right. Then the larger ones here are sort of the further away far domain, which is further away means that I can probably cluster a larger number of sources with the same error, and that's in fact what one can do. So you see, the tree structure allows you to very easily find what's near and what's far, and it also allows you to write a program where you can, at order n, very quickly determine the whole relationship of the things in space, of the sources in space. This is a two-dimensional effect, and if it's a a two-dimensional example, and if you have a 3D problem, then you would simply have 8 nodes coming out of each other node in the tree. So you can still draw this kind of flat tree. The only difference is in 1D you'd have a binary tree, in 2D a quad tree, in 3D an oct tree. But everything can be represented in the tree. And so we like to sort of describe the whole algorithm, the whole fast multiple algorithm, in terms of the tree. The tree has many functions in the fast multiple method. The tree is a data structure. The tree is also this kind of representation of space, but it also allows us to sort of visualize the whole algorithm on it. So this is what we call the bird's eye view of the FMM, of the fast multiple algorithm. At the root level, at the leaf level, which is the finest level of the tree, that's where the sources, the particles reside. One is going to do an operation which is called the particle to multiple.